In a previous video, we covered the overview of probability topics and some key definitions, and then in the next video, we covered an overview of probability rules and focused on the conditional probability rule. In this video, we'll do the addition rule. Sometimes we call it the OR rule because when you can word your compound event using the word OR, you can use the addition rule. This usually applies with a single trial. We know this means the probability of A or B or both in the same trial. So the formula was to add up the probability of each event and then subtract anything that overlaps. Another way of looking at this is to count up the total number of A outcomes, count up the total number of B outcomes, add them together and subtract the number of outcomes that were counted twice, and divide all the sum that you did here after subtracting any overlap, and divide that total by the total number of possible outcomes. When we're doing the addition rule, we need to consider whether there's overlap. That means, are they mutually exclusive events, or do they have an overlap? Mutually exclusive means two events are not able to happen at the same time. So what we say is that the probability that they both happen at the same time is 0, right? It's impossible that they can happen together at the same time. We can state this in symbols like this. Sometimes you'll see the word and there. I like this better because it represents intersection, which I think is more specific. It's also referred to as disjoint if the two don't overlap. So events that are not mutually exclusive are called overlapping. That last point there, just as a reminder, I know we've already said this, that we want to consider the mutually exclusive when we're doing the addition rule. But this is an important thing to keep in mind because you don't want to confuse it with another rule we're going to be doing, which is the multiplication rule. When doing the multiplication rule, we don't deal with mutually exclusiveness. We deal with another concept called independence. So here's an example of two events that are overlapping, right? So they're not disjoint, they're not mutually exclusive. So the overlap or the intersection of A and B has one outcome in it. The universal set is numbers 1 through 12. A has the numbers 1 through 6. B has the numbers 6 through 9. And then we have the shared space there with the number 6 in it. So if we want to calculate the probability of A or B, what we mean is that if we randomly, let's say all these digits were in a bag and we were reaching in and grabbing one out randomly, we would be happy if we picked something from out of A, or we would still be happy if we picked something from out of B, or something that belonged to both. So how many ways will we be happy? How many chances do we have to be happy? So you can probably tell that the answer is we have 9 ways to be happy. But if you calculate the probability of A, you'll get 6 out of 12, and the probability of B will give you 4 out of 12. So if you were to just add those probabilities together, you would get 10 out of 12 instead of what we know we should be getting, which is 9 out of 12. So we need to subtract off the probability of getting something that is in the overlapping region. Let's look at an example with playing cards where we want to calculate the probability of getting a king or a queen. And let's focus on whether or not kings and queens are mutually exclusive for a moment. There's all my kings. Here are all my queens. Do we have any overlap? No, because they're mutually exclusive events. So the probability of king intersected with queen is impossible, 0. What about king or red? So we have our kings here, our, our reds, all our red cards, and you can see where the overlap is here in green. So the probability of the intersection is not 0, so they're not mutually exclusive events, they're overlapping events, 2 out of 52, which would reduce to 1 out of 26. All right, now let's actually calculate the probability of drawing a king or a queen when we're only picking one card. So we would be happy if that one card was a king or if it was a queen. The probability of a king and the probability of a queen is the same here. 4 of each. So there's 4 kings out of the deck of 52, so that would be the probability of a king. There's also 4 queens in the deck, so the probability of drawing a queen would also be 4 out of 52. If we reduced this, it would be 1 out of 13. Now, it's important to have both the reduced version and the original unreduced version. Depending on the problem, sometimes it's going to be easier to work with the original unreduced version and then just reduce the final answer. So we'll see what happens here. So the probability of a king or a queen, and that's a typo, that equal sign doesn't need to be there, the P should be right here, equals the probability of a king plus the probability of a queen minus the probability of the overlap. So what's the probability of the overlap? We already looked at that and figured out that they are mutually exclusive events with a probability of 0. So the probability of a king or a queen turns out to be 1 out of 13 plus 1 out of 13 minus 0. Now in this case, I chose to use the reduced versions of the two probabilities since they do have a common denominator. I can keep that common denominator and just add the numerators and get my 2 out of 13. Now let's do, we already saw this. Okay, now let's do the probability of drawing one card and either it's a king or it's a red card on that one card. So our favorable events would be we'd be happy if it were a king, we'd be happy if it were red, and we'd be happy if it was both a king and red. The probability of a king is 4 out of 52, which is a reduced fraction of 1 out of 13. The probability of getting a red card is 26 out of 52, or reduced 1 out of 2. Now, because they have different denominators, it's going to work out in this example for us to use the unreduced versions since they have common denominators. So, the probability of a king or a red is add the probability of a king plus the probability of a red minus the probability that they are both at the same time. And remember, we already figured out that the probability that they are both on one card, that one card can be a king and also red, is 2 out of 52 or 1 out of 26. So our calculation looks like this. The probability of a king plus the probability of a red card minus the probability of both in the same card gives us a total 32 out of 52, which reduces to 8 out of 13. Okay, a little instant replay there. In the next video, we're going to go over the multiplication rule. We'll do some examples. It'll be great. I'll see you over there.